evening to one and all. Welcome to yet another topic in real number system. We have seen certain properties of modulus functions, right? And I hope whatever I have left for you all to prove. In fact, I think I had done most of the properties, but if at all I have left something for you to prove, kindly do that. With that, let's kind of move ahead and do more things. So let's kind of I would want you to do this. Let's kind of do this example. Show that. I'll leave it as an exercise for you. Show that modulus of x is less than y if and only x belongs to the interval minus y, open interval minus y. Right? Please do this. So let's write some remarks. First thing you need to notice in R is when you say modulus of a minus b, that is precisely the distance between a and b. Okay, I hope the idea is clear. A minus b is the distance between A and B, right? So let me write this as distance between A and B on the real number line. Right? Then when I say modulus of x, the distance of any real number from the origin, so from 0. Okay, so you need to take care of these two facts, that whenever you have modulus of something less than a positive given number, so when we say that x minus y, you encounter this many times in your course in real analysis. When I say x minus y less than epsilon, it means that distance between x and y is less than some positive number. Okay, right? So that's the idea I would kind of like to look at. Well, now let's look at more things. Definition. Okay, what does we have? A subset. So this is like we have already seen something as boundedness. It's bounded above, bounded below is called as bounded, but we put it as more precise. Okay, a subset A of R, a non-empty subset. Let me say this empty subset is no point. A non-empty subset A of R. Okay. Is said to be bounded, is said to be bounded in R, because if and only if it is bounded above as well as bounded below. Right? So any subset which is bounded above as well as bounded below will be termed as a bounded set. Right? That is a subset of R, and we put it in form, is bounded if and only if there exists alpha comma beta in R such that alpha is less than or equal to x, less than or equal to beta for every x. So you should be able to find two real numbers such that every x lies between those two real numbers, right? Isn't it? Geometrically, if we speak, A is bounded even if A is contained inside alpha beta, where alpha and beta are finite. If we view this, you know, so you should be able to contain it inside an interval. Closed interval, open interval doesn't really matter, but your endpoint should be finite. It's a finite real number. That's the idea. Okay, you should be able to put it in an interval, right? As long as you can put it in an interval, bounded set can put it inside an interval with finite numbers. Both the endpoints. Let's look at it here. So, dramatically it means, suppose I have A here, then alpha would be somewhere here. Sorry, let me take beta to be the upper bound. Beta would be here, and all the numbers would be less than beta, and alpha would be here. Right? All the numbers would be greater than alpha. So, this set is inside the interval alpha. Okay, let's look at here. A subset, I'll just keep the non-empty one, is bounded in a even only if there exists a positive real number such that modulus of x is less than the prime for every x. Alright. So what does this say is the same idea as what we have done, but in a different way. A subset is bounded if and only if it can be put inside an interval of the form minus and common. Okay, right. So that's the idea. Okay, let's look at this. Okay, let's look at this proof. Suppose okay, so there are two parts here. It's bounded, then this is true, and if this is true, it's bounded, right? Both the ways we have to do it. Okay. So let's get this idea quickly without wasting much time. Okay, so suppose A is bounded enough, then by the previous definition we know that this implies there exists alpha beta in a such that alpha is less than or equal to beta, alpha is less than or equal to x less than or equal to beta, isn't it? Right? And this is true for all x. For any x, it would lie between. So this would work as a low bound, that would be working as a upper bound. Well, in fact, they would work as supremum and minimum, because completeness of R tells us that any set bounded above is supremum, as well as so that can be done. So I need a positive real number, right? And I have already two real numbers, right? With that, how can I find positive real number? I want a positive and right? So let's look at this one. Let m be equal to maximum of I can't take alpha beta because alpha beta may be negative. I don't know. So let me put them in the modulus one. I take the absolute value, right? Okay. Right. Both the things cannot be zero. Remember that. Both the things cannot be zero. Otherwise, x will be zero. Right? So one of them has to be positive, right? That means one of alpha beta has to be non-zero. In that case, whatever the number zero, number non-zero is, modulus will be positive. So in this case, clearly let us write this. M is bigger than 0, right? So let's put this in a note that okay, how do I put this? Okay, so I want to get it in a way I can put this as. So let's look at this one. So there will be two cases. Okay, first of all, let's consider this. If alpha is less than equal to x, less than equal to alpha is less than equal to x, less than equal to beta, then since let's write this, since alpha is less than equal to x, less than equal to beta, this would imply that minus alpha, if I multiply throughout by minus 1, I'll get reverse inequality. That's one thing. Let's take two cases on x. Suppose x is positive. Okay. Then modulus of x is same as x, but x is given to be less than equal to alpha, beta. Sorry, x is given to be less than equal to alpha. So this is less than or equal to beta. But we know that now any number is less than or equal to its modulus. Right? Any number is less than or equal to its modulus. We have proved that because if you want, modulus of a is less than or equal to plus or minus a. So either a or minus a is always less than or equal to its modulus. And beta is here, right? So maximum of two numbers is always bigger than both of them, right? So this would be bigger than maximum of alpha, absolute beta. Or what is this? We have said this then, right? So what do we get? This implies x is equal to this, which is less than equal to this, which is less than equal to this, which is less than equal to this, which is equal to this. This implies that x has to be less than or equal to. Right? So if x is positive, what I get is modulus of x is less than equal to x. Let's take another case. Suppose x is negative. So case 1 is like, and let me write case 2. Suppose x is negative, this will imply that negative number is modulus negative of x. But we have seen that negative of x is less than or equal to minus alpha. This is less than or equal to minus of alpha. But this is always less than or equal to its modulus. Any number is modulus number is bigger than or equal to plus or minus of the same number property. Number I don't know what other property is. This is less than or equal to maximum, right? Maximum of alpha, beta. But this is then. So what do we do? This implies that. So I'll start with let x belongs to. I don't know whether it's positive or negative. I can do cases accordingly. So this implies what? This implies x is less than or equal to n. So from here, either if x is positive, still I get the same inequality. Okay, so from n 1 and 2. From 1 and 2, what do we get? Modulus of x is less than or equal to n. Right? So the direct part is proved. Let's look at the other part is 2, 3 to be proved. So we have assumed the fact that it is bounded. We have shown that modulus of x is less than or equal to for every x. Conversely, suppose modulus of x is less than or equal to m for every x in a by the property I said that if modulus of x is less than y for f, then it's even only x belongs to minus y, right? So if this is true, right, then this would imply that this was it's less than. If I put less than or equal to, then this turn into a closed term. Okay, so this implies that x would belong to closed interval minus m. This would imply that minus m is less than or equal to x. This is true for every x in it. So minus m will be less than or equal to x, less than or equal to m. This is also true for every x in it. Right? What does this prove? This proves that x is bigger than or equal to minus m for every x in it. Right? And x is less than or equal to m for every x in it. What does this mean? This means that minus m is the lower bound. Okay, right? And m is the upper bound. Like this. And m is the upper bound. What does this? This means that this implies that. Right? So that concludes the proof. So let's work out on some examples accordingly. Alright. Let's kind of see this. Example. Let's look at this. Set of all x in R, right? Such that distance between x and a, right, the same as distance between x and b, right? So distance between x and a and x and b are same, then x must be the midpoint, right? Isn't it? X must be the midpoint, right? Okay. A plus b, right? So let's look at this. What happens? All right. That's my A. Right. So let's kind of look at that solution. See, I don't know what are x and what is a and b. So without loss of centrality, we'll assume that a is less than b. You can just work the same proof out where you assume a is greater than b or b is less than b. Doesn't really change the fact, right? You just want to and I want to maintain intervals, right? So assume a is less than b. So my a is here. It doesn't really change anything. Where is a and b? If this is true, then it has to be the midpoint. So if this is true, so suppose I don't know where my x lies, right? So suppose x lies outside. If x lies outside A, then what would happen? Okay. This would imply that absolute of x minus a. If x is less than a, x minus a is negative, right? So this would imply that x minus a is negative. So this would mean that this is nothing but negative of x minus a, which is equal to a minus x, right? Isn't it? And what happens to x minus b? What happens to x minus b? Suppose so my x is here. Okay. Right. What happens to what would happen to what happens to x minus b? This is if x lies here, x is of course. Also, since we have seen that a is less than b and x is less than a, also x will be less than a, right? So what do we get? What do we get is modulus of x minus b would be is equal to b minus x, right? Because x minus b would be negative. Oh, sorry. Therefore, as a is less than b, right? This would imply that minus a would be bigger than minus b. If I add x on both sides, what I get is x minus a would be bigger than x minus b. Right? If a is less than b, whatever I have assumed, then if I multiply by negative sign, what will happen is inequality will get reversed. Now, if I add x on both sides, what I get is x minus a is bigger than x minus b. Right? If I'm not wrong, isn't it? Right? Therefore, if I multiply minus and again, we could have just added that would have been better instead of doing this. Just add minus x on both sides. So if I add minus x on both sides, what do I get? A minus x would be less than b minus x. Right? But what is a minus x? A minus x is nothing but modulus of x minus x. And what is b minus x? Modulus of x minus b. Right? So what do I get? Modulus of x minus a is less than modulus of x minus b. But what are these? These are all points such that these two are equal, right? So if I take x less than a, what happens is x does not belong to this. Right? I hope you are getting the point. I'm taking x less than a, and this is all points whose distance from a and b are equal. Right? All points whose distance from a and b are equal. Right? So this would imply that x does not belong. Similarly, if I take x bigger than b, so x is here, right? This would imply that x minus b is positive. So what happens to x minus b? This would be equal to x minus b. Now, if x is bigger than b, right? So also since x is bigger than b, right, and b is less than a, sorry, b is bigger than a, right? Also, what will happen is x will be bigger than a, right? Therefore, what happens to x minus a? X minus a will be x minus s as well, right? Therefore, what happens? Since a is less than b, right? Therefore, minus a will be bigger than minus b. Therefore, x minus a will be bigger than x minus b. Just a is less than b is assumed, right? So, what is x minus a? This is modulus of x minus a will be bigger than x minus a. Modulus of x minus b. So, I again get a problem that x does not belong to a because that says that both should be. Both of this should be. This will imply that x again does not belong to a. So, x cannot lie outside a and b, right? It has to be in between, right? So let me wipe this. Keep the question. Therefore, x has to belong to. So therefore, what should happen is x must be between a and b. Right? X must be in between a and b. Right? So let's do this. Let C be equal to the midpoint of A and B. So midpoint of A and B will be okay. So if x lies in between A and B, then x must be either equal to C, less than C, or bigger than C. We will take both the options that x is neither less than C nor it is bigger than C. Therefore, by law of trichotomy, it has to be equal to C. So by law of trichotomy, what should happen is x either has to be equal to C, x has to be less than C, x has to be bigger than C, or x has to be equal to C. Right? So we will take out both the options that x is neither equal to, either x is neither less than C or x is not, or x is bigger than C. So it has to be equal. So let's kind of get this idea. Case 1. Suppose x is less than c. Okay, suppose x is less than c. So c is midpoint. So suppose x is here, right? Therefore, what happen to x minus a? X minus a would be x is here. X is bigger than a, right? So that means this is x minus a, right? If I subtract a on both sides, this would be less than. This would be less than c minus a, right? Isn't it? But what is c? C is I have taken to be a plus b by 2. So what I get is this is equal to a plus b by 2 minus a, which will be b minus a, right? I hope this I'm not making a mistake. Yeah, right? Okay, b minus a. And what about x minus b? Look at this, x minus b. Again, x is here, right? So x is less than b, right? So what will happen is x minus b would be negative. This would imply that x minus b is minus of x minus b, or I can write directly as b minus x. Right? So from here, what I get is negative x would be bigger than negative c. If I add b on both sides, what I get is this is bigger than b minus c, right? Which is equal to b minus a plus b by 2. So this would be 2b minus b. This will be b minus c. Right? So what do I get? Therefore, what do I get is x minus a, which is less than b minus a by 2, right? And b minus a by 2 is less than x minus b, right? X minus b modulus. So what do I get? Therefore, x minus a becomes less than x minus b. This implies that x again does not belong. Right? If I take x to be less than c, right, x does not belong to a. Right? Similarly, I would get the same kind of contradiction if I take x bigger than c. Let's quickly work it out and let's see. Suppose x is bigger than c. Right? So let's draw that a is here, b is here, c is here. I take x here. I can't take x here, right? So we have worked out in a case wise. It's not difficult, but you need to understand that it's kind of a systematic argument, right? So suppose x is greater than c. Okay. So what happens to x minus a? Same contradiction we will get. If x is here, x minus a would be again positive. So this is x minus a, right? Subtract a, this would be bigger than c minus a, which is equal to a plus b by 2. Negative a, so this is b minus a by 2, right? And what happens to x minus b? B is again less than b is bigger than x, right? So this implies this is again negative of a x minus b, which is equal to b minus x, right? Multiply both sides by negative, so minus x would be less than minus c, right? So if I add b on both sides, what do I get is this would be strictly less than b minus c. But c is nothing but, so this is b minus a plus b by 2. So this is equal to 2b minus a. So this will be b minus a by 2. So what do I get here? What do I get here? I get x minus b to be less than b minus a by 2 to be less than, because this is less than x minus a, right? So this implies that x minus b is less than x minus a. This implies that x does not belong to a again. So either of these two cases, I get a contradiction. Case 2, right? So what should happen? By law of dichotomy, I've taken x belongs to a, right? Starting, remember that, isn't it? Therefore, by or x has to be equal to c, that is okay, right? So what do we do from here? That a is contained inside singleton, because I have taken x equal to x in a, right? And what I showed is x is this, so x is contained inside this, right? Next, that x belongs to this singleton a plus b by 2. That means it has to be this. This implies that x must be equal to a plus b by 2, right? Therefore, if x belongs to the set, it must satisfy both the conditions, right? So let us prove that. What happens to x minus a? Absolute of x minus a. This would be equal to this is a plus b by 2, right? This is a plus b by 2 minus a, right? So what I get is this will be equal to b minus a by 2, right? And what happens to x minus b? X minus b would be equal to modulus a plus b by 2, right? Negative b. So this also would be equal to wait a second, my mistake. Taken a to be bigger than a. So this would be a plus b by 2 negative b, right? So this would be a minus b by 2, but b, since b is bigger than a, so what happens to this is nothing but b minus a equal to that. So what I get? This implies x belongs to a, right? So singleton a plus b by 2, right? Both are equal, right? This is equal to this, right? So this is equal to absolute of x minus a. Make out that, right? So what do I get? X belongs to a, which implies this is contained inside a, right? So what does it mean? A must be equal to whatever a is, must be equal to this a plus b. This set must be equal to this, right? That's the whole thing, right? So it's pretty mechanical, not difficult. Only thing is you got to deal with the cases precisely, right? And you can work them out systematically. There is nothing which is difficult. Only thing is certain things you need to understand. Okay, let's be back for with more examples. Meanwhile, if you wish to try something on your own, I welcome anybody who wants to try. You can try and look at what you get. You will try this if you want, and try. This is I'm looking at all the real numbers, right? Such that x plus 2, right, is less than. Wait, I can look at this one. X minus a, x minus 1 is less than 4. X is okay. You can say that x is around 1. 1 is a problem. So this set is nothing but negative infinity comma 1 union to common. You can try this, but I'll come back the video to kind of finish this up. Okay. So that's it. That's it for today's video. Please go through that and let me know if you have doubts. And I'll be giving you lots many examples before we go to real sequences. Right. So till then, take care. Bye. Keep following. Keep learning. Thank you.